the AP questions that you did, if you did them on the My AP site. And I just want to point out to you that like it looks like you can like grab a OneNote, so you could like hand write it and then drop it in, which is probably easier than typing. So if you haven't yet submitted your scores for this, I couldn't grade them, even if you're like part way done. So if you guys can, if you get a chance, so okay, I see some more people have put theirs in. It's just on completion, man. I graded it like an AP thing. There's not like, it just was a 5-point homework assignment. Like, don't lose your sleep over it. I'm just trying to get you feedback as to like, okay, I did this, and then like, you know, like what would have this been, right? So like I tried to grade this as an AP grader would have, and when I assigned the points. But remember, what's a 50%? That's like 4-town almost, right? I think 50% is like right at the boundary between 3 and 4. So if like you're 50%ing these things, that ain't bad. That puts you in a good spot, right? Like don't get too frustrated about it. We'll go through these things maybe next class or something, and talk about what I saw here. So if you didn't turn your stuff in through the AP site, if you can do that here in the next couple of days. I know some of us said they did them by hand. But I think if you like scanned it, you can probably drop it into OneNote and then drop that in from there into here or something. Or if you have to rewrite a little bit of it into OneNote and you can drop it in, that's probably easier than trying to type it. In general, I had a tough time with some of our typed responses from other people. So anyways, we'll do more of these as we go, but that felt like a nice, we just did the test. I'm not going to ask you to do anything new. Let's go back and do some old stuff. But that was like a nice little fun thing. I'm sure you all had a great time, right? You know what? That warms my heart. All right, so today we're going to start chapter 9. This is the last chapter of required materials. So this will be, chapter 9 will be the last test for the semester. The hope is that we'll have this wrapped up end of March-ish, beginning of April, leaving us that last month to kind of work on review stuff and for me to sprinkle in a couple of these other topics that I think are things you'd likely see in your first year or two of calculus in college that aren't required AP questions. We'll sprinkle a little bit of that stuff in. But by the end of chapter 9, it'll just really be homework points will be all that's left to do.
How would you rate this chapter?
I don't think this is, I think it's easier than the previous chapter. It's, again, mostly application, so there's not a lot of, like, new complicated ideas. It's just kind of using the algebraic tools that we've built out so far. There's a little bit of context here, so you have to, like, kind of think about what's going on a little bit. But I think the hardest parts of this are really, like, the algebra parts, to be honest with you. Which is, if you're good at symbol pushing, should be no big deal. All right. So chapter 9 is all about differential equations. So we're going to be solving differential equations, writing differential equations, like interpreting results from differential equations. looking at applications. So we're going to start with kind of like a classic example of a differential equation, which is wanting to model population growth. So if we're talking about modeling population growth, we're really talking about a situation where there's two variables, time and population. In most cases, we assume that populations are going to grow over time. But depending on how we've set up our equation, maybe not, right? Okay, so we're going to look at two different ways of kind of modeling population using a differential equation. This first is like the ideal setting. So we're going to make a couple of assumptions. We're going to assume that the population grows at a rate proportional to the size of the population, which is probably not a far stretch, right? Like bigger populations should grow faster than smaller populations. So if that's the case, then the rate of growth, dp dt, should be some constant times the population. Right? If we say it's proportional, then it'll just be some constant factor of whatever the population is. We're going to make a few assumptions. One, that the population is non-zero, since population can't grow if there's no people. Everybody's okay with that? And then our function is the population is going to be positive for all values of t. Again, probably not hard to assume why negative population doesn't make a whole lot of sense. Now, if we assume that k is positive, then the derivative is positive for all values of t, right? Why is that? Well, because the population is non-zero and positive, right? Everybody's okay with that? So this would imply to us then our population would be always increasing. And as the population increases, so does the rate of growth for population, right? Based on the model we've just described. Everybody agree with that? Again, k is a constant, so that's always the same. If p is getting bigger each time, then the rate of change has to be getting bigger each time, as long as that constant is positive. I guess I should say, yeah, positive. Can't be zero either. Can you think of a function whose derivative is a constant multiple of itself? Because that's what we're talking about here, right? What's a function that we've dealt with whose derivative is a constant multiple of the function? Yeah, good. So like e to the t is a good candidate for this because the derivative of e to the t is 1 times a constant e to the t. So that's good. So if our population function is then going to be some kind of exponential, the p of t is what we call a solution to that differential equation, right? So what we're looking for when we solve a differential equation is like the antiderivative to that equation. Now, all of these curves that we've drawn here are all examples of possible solutions to this differential equation. What are they different by? Why are they different? Not the rate of change is not so much the difference there. It's because you could have like some constant attached to the end. That's why they're at like different heights, because you could always have like a plus c at the end that blows up when you take the derivative of it, goes away. And then so that's going to cover that stuff. Why are some down here pointing down? because we haven't decided whether k was positive or negative, right? Now, if we assume that k can only be positive, then we have, and time can only be positive, then we have everything restricted into the first quadrant, which makes sense, right, when we talk about a real-world situation. Populations can only be positive, time can only be positive. Not a big stretch there to limit this down to first quadrant. And again, why do we have different possibilities here? Just for different constants stuck at the end, different c's. So this is like the ideal, like an ideal situation for population growth. What do we mean by that? It means that we have like an unlimited environment. You have all the space you could ever need. There's adequate food supply, like there's no shortage of resources. There's absence of predators. There's nothing coming in to like eat the population or, you know, immunity from disease, again, etc. There's nothing there that's really kind of dragging the population down. Is that true to life? No, not really, right? In reality, all of these things can become limiting factors, right? So they're going to contribute to what we call a carrying capacity, like an upper bound for the maximum population can have. We're going to abbreviate the carrying capacity for a population with the letter capital M. Now, when a population is relatively small, we'd expect the population growth to behave like the ideal, right? As that population gets bigger and bigger and approaches the carrying capacity, we'd expect that rate of change to slow down. And if it ever surpasses the carrying capacity, we'd expect that growth rate to become negative to drive us back down to the carrying capacity. Does everybody agree with that? So what we're going to want to do is we're going to create a second model that kind of reflects what we think reality should be, right? So we want the rate of change to be close to the ideal when the population is small. That's what we say, approximately Kp. And we need it to be negative if the population exceeds the carrying capacity. So if we do that, we get this model. So let's think about what this is saying. We have Kp times 1 minus P over M. So when P is very, very small, P over M is essentially 0. So 1 minus 0 is basically nothing, and we're basically Kp. That's what we want, right? When P is small, we want it to act like the ideal. That's what's going on. If P is equal to M, what do we get? We get 1. 1 minus 1 is 0, so the growth rate would be 0. We call that like an equilibrium point, a place where the differential isn't changing at all. So when P is equal to M, we have a differential. What's the other value of P that causes an equilibrium point other than M? It's a der answer. 0, right? Because if P is 0 here, 0 times anything is still 0. So those are the equilibrium points. Those would be the points where you get there and you can't budge out of there. If P is bigger than M, what's going to happen? This P over M becomes bigger than 1. So 1 minus something bigger than 1 is going to be negative, which is going to give us that negative growth back down. So this looks like a really nice representation because it's kind of incorporating all the behaviors that we want to see, right? So I think we answered all these questions. So if we graphed the possible solutions, we'd have something that looks like this, right? Anything that starts below the carrying capacity can reach at most the carrying capacity, can't exceed it. anything that was exceeding the carrying capacity is going to be drawn back down to it. And why do we have multiple different bands? Because you always could have like a plus C that gets obliterated when we do the differentiation. So we just have like these kind of parallel curves. Does this feel okay so far? We're just kind of talking right now, right? We're just getting used to the vocabulary and walking through a real situation. Okay. So let's get to some basic vocabulary stuff and like some specific numeric examples rather than just like this real world framing that we've done. So a differential equation is an equation that contains an unknown function and one or more of its derivatives. For example, if we have y prime equals xy, that's a differential equation because we have an unknown function y and its derivative. We talk about the order of a differential equation based on what is the largest derivative present in the equation. So this guy that has a first derivative would be a first order differential equation. If this had y prime and also y double prime, it would be a second order differential equation. That's all we're talking about when we talk about the order of the equation, is like what's the biggest derivative involved. So we say that a function f is a solution of a differential equation if the equation is satisfied when y is equal to f of x. And its derivatives are substituted into the differential equation. So for example, if we take this piece up here, if y equals f of x is a solution to this guy, y prime equals xy, then the derivative of f should be x times f of x, which is exactly what we're seeing here, just we've replaced y with f of x. Everybody's okay? Jillian?
Wait, so f of x is not equal to y, or, oh, it is, okay.
If y equals f of x is a solution,
okay.
So f of x would be like a specific equation, like,
Right.
you know, e to the x, or sine x, or, you know, x squared plus 7x plus 15, or whatever. You know, like, it'd be something specific, where when I take the derivative, it is equal to x times the function, right? To solve a differential equation, we're expected to find all possible solutions of that differential equation. But we've already kind of done this, at least in a simplistic sense. So like if I know y prime is equal to x cubed, and we want to solve this for y, we just integrate both sides. The integral of y prime is y, and the integral of x cubed is x to the fourth over 4, and we put a plus c at the end to represent all possibilities. This would be a solution, or represent all solutions to this differential equation. So far, so good?
So you just integrate the f of x.
Well, this was just an example. This is just an example. One specific example. It was unrelated to the previous one.
Oh.
This would not be trivial to do.
Okay. That would be complicated too.
Very likely, yes.
Okay. But for the y prime equals x to the third, is that a differential equation?
It is, because it involves the derivative of y, and we'd have like a y to the 0 over here if you wanted to think about it. Like it does have a y in there, just like, it's just like the simplest version. Why is this one so easy to do and this one I say, or I claim was going to be much more complicated? It's because it's already separated where the y's and x's are on opposite sides of the equation. Here you'd have to move the x's and y's so that they're on set. We'll see this. This is coming. When we talk about separable equations in 9.3, we're going to deal with how to do something like this. We're not really there yet, though.
For this one, why did it work just to find the integral?
Well, what we're looking for is an equation y that's going to satisfy this.
Oh.
So I just integrated both sides. That's going to get the y by itself, and we're good to go, right? Does that feel okay?
Yeah.
Okay. Again, this is the foundational chapter or section. So like, if things are hazy or they're not really making sense, or you need to talk it through, let's do that, right? We have lots of time, so we're doing good. Talk it through. It's important that we understand what's going on, and we build out our intuition as to what's going on. All right. Let's show that every member of the family of functions y equals yada, yada, yada is a solution to the differential equation yada, yada, yada. Okay. So what I need to do is I need to show that the derivative of my solution is of this form, right? So I need to show the derivative of y equals 1 plus c e to the t over 1 minus c e to the t is of the form 1/2 y squared minus 1. So what I'm going to do is I'm going to start just by differentiating my solution, right? So if I want to take the derivative of 1 plus c e to the t over 1 minus c e to the t, what do I need to use to do that? Not L'Hopital, because we're not doing a limit. The quotient rule, right? Because we're just doing a derivative here. Everybody's okay with that? How do I do the quotient rule? The derivative of, okay, derivative of the bottom times the top. Are we sure on that? You think so too? Yeah, that sounds, it's the derivative of the top times the bottom. Yeah, d high times d low, right? And then minus the derivative of the bottom times the top over the bottom squared. Everybody okay there?
What is like c and y?
Well, e to the t is a function, right? The c is a constant. So like when it says every member of the family of functions, the c is what's going to be different, right? Like if c is 1, that's one possible solution. If c is 2, that's another. If c is the square root of 7, that's another. If c is negative 13.6, etc. Those are all solutions.
If like e was like, let's say like x squared, x squared, 2x.
Yeah.
Yeah. Okay.
Yeah. It's just that the derivative of 1 plus c e to the t is just c e to the t, right? just the 1 plus goes away. Is everybody okay with that?
Do you mind explaining why you wrote the notation of the y prime is equal to dy dx?
Well, because I want to eventually do this, right? So I started by showing y prime, and that's the same thing as doing the derivative of y with respect to t, because there's a c in here also that also kind of looks like a variable. So I want to be specific about what I'm differentiating with respect to. And then it's like, okay, and the y in this case is the 1 plus c e to the t over 1. And so I put that in, so I have d dt of that y. Just trying to be like really specific. So if you go back and look at this, it's like, okay, differentiating with respect to t. That's the y, okay. All right, so let's continue simplifying here. What do you guys want to do to simplify this? I mean, all those things are probably fine ideas. This is what I noticed, though. That's a common factor, right? And then this negative is going to just kind of like, oh, I have negative and a negative. So they just kind of like cancel each other out. And then those guys cancel. So that's what the derivative looks like. But I don't know that I have a good way to get that into turn that into 1/2 y squared minus 1, right? Anybody got an idea of how to do that? I looked at it for a while. I don't have any good way of doing that. Okay, go ahead, Victoria.
What did you do with you just cast out 1 minus c?
Yeah, because I have a minus and a plus.
Would it be like that?
Okay. Oops. So over here, these were both minuses, right? So minus times minus is just a plus. So I have 1 minus CE plus 1 plus CE, which is what I wrote there. So I have the
Right there you have plus 1 plus c.
Yeah, I have 1 minus CE plus 1 plus CE. Is that?
Always plus.
Is that okay? Okay. Yeah, if you missed something or you were not sure on the algebra, or if you just need a minute to process, like, let me know. We're not in a huge rush. Elvis?
I feel like you have to y start.
Yeah, so you'd have to somehow figure out something to do with the y from the start. Here's what I did, which I think is probably the easiest way to do this, is I'm now going to jump to what's given to me as the derivative. I'm going to plug the y in there and see if it simplifies down to this thing and just kind of meet in the middle. That to me felt way easier than trying to mess around anymore with this thing, because I did not see a good way of turning that into 1/2 minus y squared. And I think you guys had suggested to like FOIL that stuff out or whatever. It would be okay. You should get the same thing. Oops. My goodness, guys. Oh yeah, that's right. That's fine. 1 plus 1 is 2. Yeah, what's
I
up?
have a question about like what he did with it, because it's like in the fifth quotient rule, it's like minus the, and then like when you factored it right, but then how did the last like 1 plus c to the t not become negative?
Okay. So we had this, right?
Right.
Negative of a negative is
A positive.
positive.
And it doesn't carry over to the other like 1 plus c to the t after you just.
I canceled the negative. It can't like make something else negative and then cancel it also. Like that's not how it works. If I have like 2 times negative 2 times 4, doesn't mean that I get to do this and this to it, make it 1 times 2, right? Because that's what you're talking about doing, right? That's not how that works.
Okay.
Is that, you see what
Yeah, that makes sense.
Okay. Sometimes it's just like, I have to give you like the dumbest possible explanation. And it's like, oh, yeah, I don't mean the dumbest, but like something that's like ridiculous. Like, oh yeah, I would never do that. It just, you have to peel away back to like elementary math. And it's like, oh yeah, that's the same thing I'm trying to do here, isn't it?
I told you.
You okay?
Oh yeah.
Okay.
I was just thinking of it too.
Oh, I get that.
How do you feel about it?
All right. So here we are, right? So I'm just trying to meet in the middle now with the two things. I took the derivative of the general solution, and then I'm taking the given derivative and plugging the y back in and seeing if I can get them to equal the same thing. So I'm going to FOIL that piece out. And then I'll make a common denominator, which would be 1 minus c e to the t squared. I like where things are heading. It's going to always get worse before it gets better. Let's see, I'm going to have a minus 1, and then a plus 2 c e to the t, and then a minus c squared e to the 2t. And that's all still that. And let's see, those cancel out, those cancel out. And I'm left with 1/2 times 4 c e to the t over 1 minus c e to the t squared. And those are now the same, right? So it's party time. We did it. We showed it. Had to do a little work. The algebra is not trivial, right? That was probably rather challenging algebraically. But it's okay. It's okay. All right, so it then says find a solution to the differential equation that satisfies the initial condition y of 0 equals 2. So we were given that any solution is going to be in this form, right? So we're going to just say, okay, well, if y of 0 is 2, we're going to find c. So we're going to find a specific solution now, given a initial condition. Everybody's okay with that? So in place of y, I write 2, and everywhere where there is a t, I write 0. Oops, that's a minus. What's e to the 0? Yeah, so c times e to the 0 is c. Or e to the 0 is just 1. Okay? Everybody's good with there? How do I solve that equation for c? 2 equals 1 plus c over 1 minus c. Multiply both sides by 1 minus c, right? So 1/3 is c. So my equation then, my function, my solution to that differential equation with the given initial condition should be this. Elvis? I made a common denominator with the 1. Is that good question? Now, that answer that we've written down, perfectly acceptable. That's not the way Mr. Kulik would write it, though. What does Mr. Kulik hate about this? Answer? Not the exponential in the denominator. I'm fine with that. I have a fraction inside of a fraction. Yuck. What can I do to fix that? Yeah, just multiply the top and bottom by 3. Now, if this was a free response question, they would not care. But if this was a multiple choice question, there's no way that they would write it with the 1/3 in there. You would see this form. Now, this is, I think, bordering on too difficult for a multiple choice question, but you never know. Again, the multiple choice question should be quickies, or should be a quick way to do them for the most part, because you don't have a ton of time to do them. What do you guys think? So we're just going to be looking at 1 through 13 from this section. Which is pretty cool, because that's not a lot of questions. So just to take a quick look, since we got some minutes. So number 1. How do you do that? Let's just do it together, right? We got some time. 15 minutes or something left, right? We got some time. Let's do a couple of these problems together, right? Absolutely. Why not, right? Help you guys out. So this is what we're going to be using. But instead of y prime, what do we need to put in there? The derivative of that, right? Right? So what is the derivative of 2/3 e to the x plus e to the negative 2x? Good. Is everybody okay with that? Basic chain rule. So in place of y prime, I'm going to write 2/3 e to the x minus 2 times e to the 2x plus, and then instead of y, I'm going to write 2/3 e to the x plus e to the negative 2x, and that should equal 2e to the x. Is everybody okay with what I did? Okay. Let's distribute that stuff through. Okay. And I notice, hey, those guys cancel out. How do I add 2/3 e to the x plus 4/3 e to the x? They already have a common denominator. 6/3 is just 2. So we're done. We did it. We showed it. Right? Is everybody okay with like how to do one of these show that questions? You're basically just like, okay, I'm just going to take my differential equation, plug in the actual values for y and y prime, and just show that it is equal. Just doing some algebra at that point. Certainly. Say hi to Luke if you see him. Okay. Yes, sir. Oh, yeah, if you have 9:30 people for band and choir, if you need to leave for that, you're dismissed. Yeah, and thanks for reminding me. I totally forgot. Yeah, take care. Good luck. Hit those notes.
Thank you.
You're welcome. All right. Number 3, part A says, what values of r does the function y equals r to the x satisfy the differential equation 2y double prime plus y prime minus y equal to 0? How would we start doing this one? Well, I know I'm going to be using this, right? I don't know yet y prime or y double prime, correct? So we have to calculate those. Okay. So what's the derivative of e r to, or e to the rx. Okay, r times e to the rx. And y double prime is going to be the derivative of r e to the rx. What's that going to be? R squared e to the rx. Notice that we didn't have to use the product rule there. Why not? Because r is a constant, not the variable. So now I have everything I need to be able to do this. Okay, what are we solving for here? Again, what's the question asking us to solve for? Now we have an equation that's equal to 0. It's asking us to solve for r. Okay, what should we do to do that? Yep. Find a value for r where this function satisfies that differential equation. So we're basically just solving for r here. What's that, Alexis? Factor out an r. Well, this last term doesn't have a coefficient of r. Yeah, let's factor out e to the rx. That's the ticket. Everybody's okay there? So then we can set up or use the zero product property to set up two equations. What's the solution to e to the rx equals 0? Should be able to do that in your head. It's not 0. Elvis, you're going to say something? 10? It's not 1. It's very easy. There's no solution to that. Can an exponential equal 0? Not unless its base is 0, which it's not. We have e to the rx, right? If you tried to take the natural log of both sides, the natural log of 0 is undefined. So that would have been acceptable as well. So all my solutions are just going to come from this quadratic. How do you want to solve this quadratic? You could try to factor it. I think it should. You have to be a little bit careful because the leading coefficient is not 1. So you got to do this a little bit guess and check, correct? Yeah, I think we have to do that one, right? You could also use the quadratic formula if you're having trouble factoring, or if you ran into something that couldn't be factored, which would not be unreasonable. So there we go. My values for r could be 1/2 or -1. Okay. So that's part A. To part B over here. It says if R1 and R2 are the values of R that you found in part A, so that every member of the family of functions y equals A times E. Now R1 is going to be 1/2, so I'm going to write that in, plus BE to the -1, I'll write that in, is also a solution. Well, what am I going to do? going to show that that value for y satisfies this differential equation. So what am I going to need to do that? I'm going to need y prime and I'll need y double prime and now it's just like a bunch of crappy algebra, right? So let's see. I'm going to distribute through my 2. Here I'm going to drop my parentheses since I don't need those. And here I'm going to distribute through my negative. And then let's see. I got 2b to the e to the negative x's. I got a negative b to the times e to the negative x, and another negative b times e to the negative x. So those all cancel each other out. Then I have a over 2 plus another a over 2. That gives me just an a e to the 1/2 x. And I have a minus a e to the 1/2 x. So those cancel each other out. And I'm just left with then 0 equals 0. Check. Since this was all still equal to 0. Sorry. Is this feeling okay on what to do with this stuff? What do you think? You want to do one more? We're like halfway done with the homework here in a second. Victoria, what's up? Are you okay? Okay. I love it. Differential equations. It doesn't say anything on my sheets, but I'm sure they'll come on and make an announcement here. Yes, Serge? Sure. All right. Which of the following functions are solutions to this differential equation? Derivative of sine is cosine. The derivative of cosine is negative sine. So we have negative sine plus sine equals sine. No, that doesn't work. B, so y prime is going to be negative sine, and y double prime is going to be negative cosine. So we have negative cosine plus cosine equals sine. No, that doesn't work.
So what are you doing?
I'm just checking this, right? So it's giving me a bunch of different solutions, possible solutions. I'm just checking them against that one. Your only answer is going to be D? Oh, okay. So what's the derivative for C going to be? Yeah, you have to use the product rule. Very good. So you have 1/2 x cosine x plus 1/2 sine x. And then the second derivative of that is, oh, Mr. Kulik again? Yeah. 1/2 x negative sine x plus 1/2 cosine x plus 1/2 negative cosine x, or sorry, probably positive cosine x. Okay, so we have 1/2 x, well, let's make it negative, and then we have cosine x, and we have plus c, or plus y, which is 1/2 x sine x. Oops.
Why did you get rid of the 1/2?
I added them together and just wrote it as 1 cosine x. And this should equal sine x. Well, these guys cancel out, but cosine doesn't equal sine. Elvis, I think you're right. Or D is going to be the only one that works. Oops. So y prime, and then those will just add to give me a single sine x plus and that one does it. Yay! What do you guys think? It's not bad, right? Like, some of these things are like, you have to do some serious symbol pushing, but like the amount of like complicated calculus going on is pretty low. It's telling you exactly what you need to do, right? The problems are telling you exactly what you need to do. You need to understand what the question's asking you to do. But after that, it's just a matter of pushing symbols until you get what you're supposed to get to come out, right? That'll be very much in keeping with the rest of this chapter. So